Hi, I'm Ahmed Daud, and in this session we will see regularization. Okay, so last time we were seeing that when we have some sort of complex model, sometimes we fall into a overfitting. Our model is capturing all the training data points, even small variations also, but not able to generalize the future data points, or you can say test data points. In this way, we can say that our training error is very less, but our testing error or error on test dataset is very high. In other words, you can say you have low bias but high variance. Okay. That case, we usually say that our model has overfitted or overtrained on the or overfitted on the training data points. Okay. Today we will see how we can avoid this type of overfitting, and this process we usually call as regularization. Okay, so before going to start this session, I want to elaborate. We will have three lectures on that regularization. In this session, we will see how and what is actually the regularization is. In the next session, we will see what are the types and famous type of regularization, which will be rich and lasso regularization. We will also see these two regularizations in more detail by some visual representations. In the session or third lesson, or you can say in the third lecture, we will do some code on the Jupyter notebook and try to see how we can implement regularization practically. Okay, before going to start regularization, actually I want to give you a recap what is actually the mean square error, and in the training phase, for what purpose we usually use mean square error. Okay, so here you can see on the screen sum of squared error or mean square error is generally the same. Just divide the mean square error by the number of points. We will get mean square error. Okay, divide the sum of square error by the number of points. It's the difference between the actual value and the prediction value. Take the squares, add all the points, differences of all the points, and then divide by the number of points. We will get a mean square error. Okay, this is mean square error. Here I have representing this prediction or y cap in this form, where we have the expression in the form of sigma. Okay, usually we have expression like that: theta 0 x 0 plus theta 1 x1 plus theta 2 x2, and you can represent this in this way. I have discussed it a lot of times. From j0 to j, let's say we have uh, just two features here. So 0, 1, 2. So here will be j, and x0 in this case always equal to 1. Okay, this x0. Theta 0, you can say it's an intercept, and theta 1, theta 2, these are the coefficients. Okay, we usually have this type of mean square error, and the purpose of mean square error in the training phase we will see also. So before that, mean square error, when you will plot mean square error uh, on the graph against the parameter values, let's say against the theta 1 and theta 2. Actually we have 3 here, but I am plotting it's against the 2 in the three-dimensional plot. Here on this axis we have theta 1, here we have theta 2. On the z-axis you can say we have a mean square error. Okay, we will have such a ball shaped uh, graph, or you can say plot here, and we are interested in the mean square error. In the training phase, we are trying to minimize our mean square error. In the training, we are trying to minimize our mean square error. Okay, so we are in case of when we are doing gradient descent, we are taking gradient again and again. We are updating our parameters, and we are going in the direction where we find our mean square error is minimum, and we reach at the minima of that function. Okay, of that plot. So we are interested in the mean square error, or we you can say we are interested in the parameter values against which we have minimum mean square error in our training phase. Okay, usually we do in this way. Okay, so this part here you can say, now we will see it in more detail. In the training phase, we are doing in this way, we are minimizing our mean square error function, which is in the form of thetas, which are actually parameters. Okay, so what actually the purpose of that mean square error is the difference between your actual values and difference between your predictions. Okay, difference between the actual and the prediction values. Now you want to minimize that difference. Okay, that's why you are minimizing this mean square error during the training phase, and you are saying that you are interested in such type of model which has parameter values. Against these parameter values, your minimum, you have minimum mean square error, or you have minimum error. Okay, your model will have minimum error. Now, due to that action, actually, when you have some sort of complex model and you have during training phase, it has try to make the difference between actual and predicted value minimum. In that case, you are fall into such type of overfitted model. If I will show you here in this way, okay, you will have such type of model in which you are also cached or captured the small variations also. Here you can see you have captured all the training data points and you have captured all the small variations also. Okay, now that the phase of minimizing the error, you fall by minimizing the error until you will have almost zero error. You will fall into such type of model which is overfitting your training data points, not generalizing your training data points. Now our aim is to avoid that type of overfitting, so that we, instead of this type of model, we should have this type of model in which our model should generalize our data points so that we can our model can predict more you can say concisely or precisely about the future data points. Okay, or you can say our model should perform well on the test data points. Okay, sometimes for the that case, when you are using some polynomial high degree model, like here you are using let's say a degree 5 model, then you in the case of when you are doing some regularization, you are decreasing your polynomials degree to, let's say degree 2 polynomial. Okay, you are making your model from complex model to you are moving towards the simple model. Okay. Now, last time I also have explained that you can do it by manually. That if you are increasing your degree, you are getting such type of model that is overfitting the training data points. Okay. Now you can do manually that you decrease the degree, and you will maybe you will get some optimal model. Okay. But if you are using the model like a linear model, or let's say linear regression, or you in some sort of like you are doing some classification problem, and in the case of classification there is a model which is logistic regression. So in that case, maybe if you are not using polynomial model, you are using linear regression or logistic regression. In that case, you cannot do manually by decreasing some degree you can get an optimal model. In that case, you have to or regularize your model to avoid the overfitting problem. Okay, so in this way, you can say that your aim is to reduce the complexity of your model, and you want such type of model which is not too simple, such type of model which is generalizing your training data points. It will have some bias and it will also have some variance. Okay, now we will see how we can do that. Here I was saying that the action of minimizing mean square error led to the part of you led to the overfitting problem. Now what we will do we will add some penalty to this function. Okay, let's say you have your cost function. Previously you have your cost function mean square error. Okay, now you will add some penalty to your mean square error. Okay, you can say you have instead of this function mean square error, you will have a function which is mean square error plus some penalty. Okay, now this part is responsible to add complexity, or you can say this part, when you are minimizing this error, you are going towards the complexity of the model. Okay, now this this factor will work in this way. It will reduce the complexity. Okay, you can say it will reduce the complexity. Now now during training phase, you have such type of cost function which is which has in the cost function you have both factors. One factor effect in this way, it increase your complexity of your model. Okay, and one factor is work in this way, it reduce the complexity of model. Now how you can control how much complexity of your model we should reduce? Okay, there is a parameter which add here. Oh, sorry. Okay, so a parameter is added here again along the with the penalty. Okay, so this parameter controls how much we should reduce the complexity of model. Okay, now instead of just this function, or in other way, when you are doing regularization, you will convert this cost function which was just a mean square error. You convert this cost function into the cost function which will have mean square error plus lambda into some penalty. Now this penalty, when you penalty will be the function of your parameters. Okay, now I will explain how this penalty will reduce the complexity of model. Okay, now before going to do towards that, how penalty reduce complexity, I want to elaborate what are the parameters. Again, if I will show you here, let's say you have equation like that: theta 0 x 0 plus theta 1 x 1 plus theta 2 x 2. What exactly the theta 1? Like this one is, you are sure that this is intercept, and this is just a value 1, and this is intercept, let's say. Okay, now these are the coefficients. Okay, these are the coefficients. Now theta 1 and theta 2 are coefficients. Okay, and in other words, you usually say that these are the slopes. Okay, these are the slopes. When you have higher value for that slopes, then your model will have sharp angles in their model. Let's say here you can see you have a high values in the theta 5, theta 4, theta 3, theta 2. Like you have, if there are two possibilities, like if you have multiple parameters. Okay, in that case your model can be complex. Or if you have higher values or high value parameters, then your model can be complex. Okay, here you can see there are sharp slopes here. Your model is abruptly changing here to its direction, then again changing its direction. There's sharp slopes in your model. Okay, now in two ways you can do that. One way is to reduce the parameter values. These are the parameters. Okay, Sometimes, usually we don't do on the intercept. Sometimes you reduce parameter values, okay, to some extent, or sometimes to you reduce the parameter values to equal to zero. To you make some parameter values equal to zero. Okay, so in this way you reduce the complexity of your model. Keep in mind, these coefficients are actually the slopes of your model. Okay, now you can reduce the complexity by reducing the values of parameters, the values of coefficients, or by eliminating some coefficients. Okay, eliminating mean to make some parameters equal to zero. Now here I was saying how penalty reduce the complexity. Now penalty, we usually have a penalties, if I will write in this way. We usually have, for penalty, we have a function of p norm. We usually use p norm function of the parameters. Let's say, what is p norm? In mathematics, norm is actually uh, is a function from real or complex vector space to some sort of non-negative real numbers. Okay, it is a function. Euclidean distance is also an application of L2 norm. Okay, so here if you want to see how p norm is actually, if you will see the p norm of your theta, let's say this is theta, and you have total coefficients in the form of theta. You have two coefficients here, theta 1 and theta 2. Okay, like here you have two coefficients. We are not considering intercept. Okay, just you have two coefficients here. Okay, so this will become, in the case of if you are taking a p norm of that theta, it will be like that. If you will see j is equal to 1 to, you have total 2 here, so this will be j. You will take a power of each, you will take a power of each theta, power p, then you will add all the thetas with the power p, then you will take a root of the whole expression, p root of whole expression. Okay, in other words, you can write in this way: under root p, here will be theta 1 raised to the power p plus theta 2 raised to the power p. Here you can say p norm of theta. We usually use this function for our penalty. Okay, usually use as a penalty this function, p norm of thetas. Here you can say, like here mean square is a function of thetas, in the same way penalty will be also a function of thetas, in which we don't have any other factors like y or x. We have only thetas, we have only coefficients. Okay, so usually instead of p norm is a generalized term. Instead of p norm we have two types of penalties. If one is L2 norm, okay, and one will be L1 norm. Okay, so in case of L2 norm, we usually have squared L2 norm. Okay, if I will say you how you can write here, L2 norm will be like this. You have this sigma j 1 to 2. Here instead of p you have 2 value here. Okay, then 1 over 2. As I have told you, here we are using a squared L2 norm, so that's why total square here. When you will open that, you will have like this theta 1 square plus theta 2 square under root because of this 1 over 2, and again square, then this square will cancel out your square root. You will have theta 1 square plus theta 2 square. Okay, sometimes we have this, usually we call this L2 norm. Okay, squared L2 norm, we usually call this as squared L2 norm. Okay, so sometimes we use this as a penalty, and sometimes we have, in case of L1 norm, we have like this, j 1 to 2 theta of j. Here we have absolute, just absolute. We don't have, because of just 1, so we have no any power on the parameters. Like if I will say you theta 1 absolute and absolute of theta 2. Sometimes we use this as a penalty and sometimes we use this as a penalty. Now, when we use this L2 squared L2 norm as a penalty, we call this is a ridge regularization. Okay, ridge regularization. And when we use L1 norm as a penalty, we call that lasso regularization. Okay, now here, let's say for instance, you can consider that we are using L1 norm. Okay, so here you are having a penalty. If I will write in this way, okay, here I will write. Now, you are minimizing instead of just mean square error, you are also have added here some penalty like L1 penalty theta 1 plus theta 2. Okay, now here you can see, okay, now here you can see this factor will increase the complexity of your model. Okay, increase the complexity of your model, because when you will minimize mean square error, your mean square error will reduce the like minimizing the mean square error will reduce the difference between actual and prediction value, and you can fall into some sort of complex model. At the same time, this factor that we usually call as penalty, when you are reducing this factor, you're actually reducing the complexity. Okay, and if you will see in more technical way, you can say you are minimizing your parameter values. Okay, you are minimizing also your parameter values, like you are minimizing your coefficients. Okay, when you are adding both, okay, let's say you have a lambda. Okay, for now, if lambda is equal to 0, if lambda is equal to 0, okay, then you will when you will multiply penalty with the lambda which is equal to 0, you will have the same function that we usually have without regularization. If you have lambda value higher than 0, let's say 0.5 or 0.1, 0.2, in this way, as you are increasing your lambda's value, you are telling the function that how much complexity should reduce in your model, how much reduce the complexity in your model, you are telling about your model. Okay, now one factor is increasing the complexity of your model, and other factor that you have added in the cost function is reducing the complexity as a model of the model, or you can say minimizing your coefficient values at the same time. Now when you will add both of them, okay, when you will add both of them, you are saying that you want such type of model, such type of model which has less, or you can say less mean square error and less values for the models, or for the less values for the parameters, you can say here, or more precisely you can say for coefficients. Okay, by adding this penalty in your cost function, you are saying that you want such type of model which has less error and less values of your coefficients in the model. Okay, in this way you are artificially reducing your values of your parameters, and you are making your model less complex as compared to before. Okay, so okay, so till now we have seen that regularization is a concept in which we are avoiding overfitting. How we are going to avoid overfitting? Before that, we have learned what factor actually what factor led towards the overfitting. We have seen that during the training phase, if we have just mean square error as a cost function, when we are reducing our mean square error, we are actually reducing the when we are minimizing our cost function, we are reducing the mean square error no matter how larger parameter values we are getting. Okay, we have learned that due to that action, overfitting actually occurs. If we can control that factor, like this factor make the model complex, if we will add some penalty to that cost function, we can control the complexity of model. Then we have seen that we have added a penalty with some factor lambda which control the complexity. Okay, so we have seen that when we add both mean square error plus some penalty as a cost function, now we can control the complexity of model. As lambda will decrease, like lambda, if lambda is equal to 0, then we will have the same function that we have before. If lambda is greater than 0, then we are actually controlling the complexity of our model. We are reducing our complexity by increasing the value of lambda. Then we have seen we usually have for penalty we have p norm function, which is the function of your parameter values. We have p norm function of your coefficients, you can say. Then we have seen that we usually use two type of penalties. One penalty will be squared L2 norm, which we usually say ridge regularization. Second penalty we usually say L1 norm, okay, in which we have just absolute values of our penalty and we have added a summation of absolute values of our coefficients, you can say. Okay, so this we usually call we lasso regularization. Now, till now, I was telling you that we are just interested in the regularization of our coefficients. Okay, not in the case of we don't do regularization on the intercept. What's the reason here? Okay, we don't do regularization on the bias or intercept term. The reason is that no matters how larger the equation of model is, we have multiple coefficients. Okay, but our intercept always be equal to 1. Now, intercept is just to shift the model from, like if we have some intercept, we are shifting our model in some direction. Okay. But when we are increasing the number of coefficients, we are actually increasing the dimension of our model. Okay. So there is no need to do regularization on intercept because intercept don't make the model complex. Number of coefficient make the model complex, so that's why we just do regularization on the coefficients. Again and again, I am repeating here, if you have some polynomial model, you can do that manually. You can decrease the polynomial degree and you can get some optimal model. But in some cases, we cannot do that when we have not some sort of polynomial model or we are not figuring out. In that case, we use regularization, and regularization works in both way. Like uh, regularization also reduce the coefficient values, or sometimes it reduce the coefficient values to and make some regular coefficient value equal to 0. Okay, for the less important features. Now, in the next session, we will see lasso regularization and ridge regularization in more detail, and we will see how of which regularization uh, make the parameter values equal to 0 and which regularization actually decrease the regular coefficient values. Okay, then we will also see how by the some visual plots how these regularization actually works. So for now, thank you.